So first we need to define what a solution is. A solution can be actually in gas, liquid, or solid phase. And we have two things that sort of comprise that solution. The first is the solute. That's the thing that's of a minor composition of the whole solution. And then there's the major composition, and that is the solvent. So for example, if you have water and you add a little bit of salt to it, the salt would be the solute, the solvent would be the water. Okay? So when we talk about this, it's important to remember our intermolecular forces, because that's going to affect how things behave and what dissolves in what to make an actual solution. So let's go back and think about this. You can have ionic compounds. They have positive, negative in them. And then you can have sort of dipole-dipole type of bonds. These are two different types of dipole-dipole bonds. The stronger of those two is the hydrogen bonding. So this is technically a subcategory of the dipole-dipole bond, remember. But it's a stronger version of that. So it has strong partial positive and partial negative bonds in there. Now, this is between, or like the partial positive and partial negative are within the water molecule itself, right? So that gives this thing sort of like partial charges to stick to other types of molecules, such as other waters, right? In comparison, the dipole-dipole bond has partial positive and partial negative charges in the molecules. So that gives them pseudomagnetic types of relationships with other molecules that are similar, but it's not as strong as the partial positive negative that you have in hydrogen bonding. And then finally we have nonpolar or dispersion forces. So there's no real partial charges in these types of things. So water belongs in this category. Okay, so it can hydrogen bond because hydrogen bonding is defined as hydrogen that's specifically attached to oxygen, nitrogen, or fluorine. And obviously water is attached to oxygen. Water is sometimes seen as the universal solvent, and that's something of a misnomer, because water doesn't dissolve oil. Well, there's a reason for that. There's a term when we talk about solutions that's just simply like dissolves like. So hydrogen bonding through water can actually be used to dissolve other things with hydrogen bonds, but it's right next to that ionic type of compound. It dissolves salts well. It can also dissolve things that are more dipole-dipole, but when we say like dissolves like, what we mean is it doesn't dissolve something way over here. And ionic compounds probably aren't going to dissolve something over here very well. So it tends to be that things are just sort of right there by what you actually have in that category. Now here's what actually happens when a salt hits water. We form what's known as an electrolyte. And basically this is just a salt that is broken down in water to yield the positive and the negative charges. Now, this is kind of cool that this happens. This is very, very fundamental in the way that your body works even. So you take a salt and you put it in water, and what ends up happening is you take the positive charge, and that's aqueous, so aqueous solution, and you take the negative charge, and they sort of separate out. Here's why. Remember, water is polar. It hydrogen bonds. So oxygen has a partial negative charge. Well, when you put NaCl, that's a positive charge with the Na and the negative charge with the Cl, in water, it separates the Na and the Cl because these little oxygens with the negative charges go and surround that Na, and they just sort of hit right to it. And the positive charges on the hydrogen go and surround that chlorine. So it's almost like, oh great, you came here to play with me, and then they just sort of separate them out. Okay? So that's very important when it comes to salts. Now, not everything separates like that. Sugar, for example, sugar is a covalent compound. It doesn't have an ionic compound. It doesn't have a positive negative. It does hydrogen bond, and that's the reason why water will dissolve sugar. Water dissociates or breaks apart ionic compounds. It does not break apart covalent compounds for the most part, unless it's something like an acid or a weak acid. Now, things that are weak electrolytes, we haven't talked about acids and bases yet, but things that are weak electrolytes tend to be weak acids or weak bases. So here's what you can see for now. You see how this arrow goes back and forth? What that means is that, hey, some of that goes over there, and some of it doesn't. Or better yet, they're exchanging at a rate that gives you more of one thing or the other. Now, over with NaCl, we have a straight arrow. Here, this is going back and forth and back and forth. So what that means is that some of this will be dissociated. Therefore, this is a weak electrolyte. Now, you can put two ends of a light bulb, if they're open, not connected to each other, just open, in an electrolyte solution, and that will carry a charge because the charges are separated. So electrolytes light up the light bulb. Weak electrolytes dimly light up that light bulb because it's just weaker. Non-ionic compounds or covalent compounds are non-electrolytes. Okay, so sugar should not really light up that light very much at all. Okay. So once we do this, it's very important to realize that not all salts are equal within water because their charges are different. So we define that as equivalence. And we simply say that, sodium has a +1 charge, so it would be 1 equivalent. Calcium has a +2 charge, so it would be 2 equivalents. Aluminum is 3, this because of the charge, okay? Same thing goes for negative charges. Doesn't really matter what it is. So if Jane has a 1.2 milli equivalent of SO4 per liter of blood, how much SO4 in moles are present in 1 liter of blood? Just realize that this is milliequivalent per liter. So here we've got actually two different units for this number. So I don't want to start there. I want to start where we have 1 liter of blood. So that's why I start right here, okay? So 1 liter, I switch it to milliequivalents, and then I'm going to switch that and convert it to equivalents instead of milliequivalents. And then realize that for every mole of SO4, when we're talking about equivalents, it's 2 equivalents of SO4 because it has a -2 charge. And so that's how you can get how many moles you have in 1 liter of blood. Okay. Now, not everything dissolves in water just because it is a salt. As a matter of fact, there's a set of rules called solubility rules that defines what can and cannot dissolve. Rather yet, it's what we as humans have observed about what is soluble versus what is not soluble in water. Okay, so let's say that we have an aqueous solution of this guy, an aqueous solution of this guy. So I have something that looks like water on this side, and I have something that looks like water on this side, and I pour them together. And what they give me is a solid. This is going to look like a cloud of stuff, sort of snow, coming down like a snow globe. That indicates that that is a precipitate. It is coming out because it's a solid, and it simply does not dissolve well at all in water. This guy will, but this guy does not. That can happen sometimes, and there are certain compounds that are more prone to having things precipitate than others. Just know that that happens and what that is, okay? Okay, so solubility. As I said, that last BASF4 was insoluble. So let's talk about what insoluble and solubility types of things mean. I want to do that by talking about making good simple syrup or southern tea, whichever way you want to think about that. So when you make tea, and you're from the South, You usually start by adding sugar to water, room temperature. And you start stirring a little bit, and guess what? It doesn't all dissolve very well. So what do? You start to heat up your water. And as you heat up your water, more of that sugar dissolves. This is what everybody knows from cooking, right? Salt does the same thing. You start heating it up and it'll dissolve more. And you can heat it and heat it and heat it and heat it. And, don't get it past boiling or anything. And you start adding a lot of sugar. Well, at a certain point, you can't add any more sugar there at all. Okay? So when you get to any temperature, because every temperature has its own version of what this is, but when you get to a temperature and you can't dissolve any more of that whatever it is in that solvent, water, that is a saturated solution. It's kind of like if you take a sponge and you put as much water in it as you could possibly soak up. That is a saturated sponge. And a solution can be like that too, where the solution just does not hold any more of the solute at all. As you increase the temperature, what you're doing is you're giving the molecules more energy. Like they're going really, really fast, right? And when they're going really, really fast, they can hold more of that solute. So imagine that like juggling, okay? So you can start to juggle more and more and more balls up in the air as you get more energy and you move faster. Well, what happens then when you get all the balls in that you can? So you get a saturated solution at a high temperature, and then you start dropping the temperature back. As you begin to drop the temperature back, then imagine that you're going slower while you're juggling. What's going to happen to those balls that are up in the air? Some of them start to fall. That's exactly what happens in a solution too. That solid that can't be held anymore in the solution will fall out. This is exactly how you make rock candy. You dissolve in a whole ton of sugar at a really high temperature, and then you start bringing that temperature back. And what happens is the sugar will crystallize into little crystals and give you like a solid as it comes back down to lower temperatures. So we call a solution that has the most amount of solvent it can hold at any temperature saturated. As you lower the temperature, that solution would then be supersaturated. So it has more in it than it can possibly even hold in it. And so something's going to eventually fall out. Now, if you have just a pinch of something, or you have less than what the solvent can hold of a solute, then it's simply unsaturated. It doesn't have everything in it just yet. Okay? That's exactly what those mean. Now, Henry's law is very similar to this with gas. If you put pressure of a gas on top of a liquid, it will push that gas into the liquid. And when the pressure is released, because you know what it's like when you open a soda can, it goes psh, right? It releases that air immediately. Now the gas that's been trapped inside that liquid starts to seep its way out, and that's all the little bubbles are in your soda, okay? This also massively affects divers, because as you go deeper down into the ocean or wherever you are diving, you can actually get nitrogen trapped in your blood. That's nitrogen narcosis. Okay. Other things I want you to be aware of with solutions. First is colloids. Colloids are like chunks of stuff. They're not necessarily dissolving stuff. It's more like a suspension. You mix something up enough to make it not settle. You know that sand and water will settle. If you get tiny, tiny particles of mud, then maybe it will still sort of get in that solution. Milk is a colloid. Milk is milk fat sections, and it is little solid chunks, but they're so tiny that they make a suspension, or they mix and they stay that way. Okay, so that's what a suspension sort of is. Mayonnaise, milk, that type of thing. These things, if you leave them sitting for long enough, they will separate. Okay, Thank you very much.